function of porosity, and usually if you use these structures, usually the provider, the company that provides you with these boulders, gives a direct indication of permeability. Especially if they are tripods, if they are regular structures, it's the company that makes them that gives an indication of permeability. So permeability is P then, and then there is a bypassing factor P, which is evaluated.
To calculate the porosity, if there are, for example, 4 windows, then the formula would be 4 times AW divided by total area.
So, sorry, can you say again?
If there are, for example, 4 windows.
4 windows, yes.
So it would be 4 times
Yeah,
AW.
yeah. W is the total area of the windows. Okay. If you have any other doubt, please.
Permeability is functional porosity, and porosity is the ratio between AW and AT.
Yes, in this case you may define porosity in this way, but keep in mind that porosity usually is defined for porous media, not for regular structures, okay? And porosity, as you may know, is defined for a generic media or a soil, is defined as the volume of voids divided by the total volume. So you may extend this definition to the case of structures with windows, volume area of void divided by total area, but I wouldn't use the term of porosity in this case, okay? Because porosity means pores. Windows are not pores, okay? Yeah.
I did not understand when you say that we take the perpendicular area to the direction of the wave.
Yeah. Usually you have to define a direction where to estimate this area, because usually we estimate these areas in the transversal direction of the structure. Okay? Because if you refer to another direction, of course, there is another area of the structure. So if you project this structure in another plane, you get a different area. Okay? You have to define what is the plane where you are measuring these areas. And the plane is that is in the longitudinal direction of the structure, and you measure the areas perpendicularly to that direction, longitudinal, okay? Is it clear for everybody? Okay. Okay, now, if you look at what is written in the web page, it is more or less the same thing. P is estimated depending on the shape of drawings, and in particular the presence of apertures. I call them windows, so you can call them windows or apertures in their cross-shore direction. Here it says cross-shore direction to mean the longitudinal direction of the drawings, okay? P values are suggested by the literature for typical drawing shapes, which is more or less what I told you. Drawings made by boulders have a p-value that is close to 0. Fine. The actual volumetric sediment transport in the drawing is related to the calculated potential rate as the multiplication of original sediment transport times F. F is computed in this way, you see here. So F is equal to P, which multiplies 1 minus B plus B. The bypassing B is usually determined according to empirical formulas. It's a bit, it varies between 0 and 1. So if the groin is very long, you have B equal to 0. If the groin is short, very short, B is close to 1. So based on your precautionary attitude, depending on the type of design, you have to empirically identify a value. So let's look at this formula up there. You see that there are two components. that form this fraction. And the two components are the second given to bypass. If bypass is equal to 1, it means that you don't have anything passing through the groin, because everything is bypassing. So if bypass is equal to 1, you see that P is ineffective, because P regulates the passing through, and you get F equal to 1. Good. If bypassing is equal to 0, then the only action is the passing through, which is given by P. Okay, so the two extremes are bypassing 0, and then F is given by only P. If bypassing is 1, F is given by only B. Of course, depending on B, you regulate the compensation between the two components. So from this you understand that in a way B is a parameter that can be determined with some uncertainty, because if you make a mistake, it's compensated by the other component, provided, of course, P is large enough. As I said, there are two components, and the components given by P, the passing through, is related to the amount of the bypass and related to P itself. Okay. It's a very simple formula, but I want to dedicate some time because you know, it's not immediate to understand. And then once you have the F value, you just correct the long short segment transport with this relationship. So in the model, you remember that we have a way with by knowing the energy of waves to compute the long short segment transport. Once we computed it, we reduce it according to the presence of noise. You may say there is a lot of uncertainty in there, and particularly in the estimation of bypassing. Of course, while in the estimation of permeability, we have some guidance. In the estimation of bypassing, everything depends really by a series of processes which are the characteristic wave behaviors, behaviors of the long short segment transport as a whole, shape of the beach. So this is more difficult to understand. In order to get a perception of bypassing, what you could say, what you could do is to look at what happens nearby, if there are other groins, if there are other batteries of groins. You may try to understand whether there is indeed, there are signs of bypassing. And for instance, you may look, if there is bypassing, what happens basically? You have segments that pass through, and then after the groin, there is less turbulence, because the strength of the wave slows down, and therefore you have the position here. Just behind the groin, you find some sand. If you find some sand that is already placed behind the groin, close to the toe of the groin, close here, then this is a sign of some bypassing. And you may look at the amount of sand that is displaced in a nearby groin, try to understand whether there is some bypassing. If there is no bypassing, you don't find any sand here. But of course, this is, you may say, there is a lot of uncertainty. Yes, that's true, but there is to say that these components compensate each other, and there is also to say that, you know, these are interventions that can be corrected later on. If you realize that the groin is too short, you can continue it later on. Or if you realize that the groin is too permeable, you can reduce the permeability in some way by putting jet sticks, by trying to reduce it by injecting, for instance, concrete into the groin. There are some adjustments that you can make. Keep in mind that coastal engineering, with respect to other branches of engineering, it's more empirical. You already realize that we make a large use of empirical formulations. And the reason is that, you know, these processes are difficult to model. There is a lot of uncertainty, which means randomness. And if you think at waves, by definition, we know that there is a lot of randomness. the summation is not necessarily equal to 1. It's equal to 1 only in the extreme cases where you have P equal to 1, and if you get P equal to 1 and P equal to 1, you have 1, okay? Because you see that if put you both of them to the unit value, you get 1. If you put B to 0 and P1, again you get 1. In general, if you have B that is between 0 and 1, and P that is between 0 and 1, you get IF that is lower than 1. In general, I would say yes, let me think about it. Yeah, let's say that, yeah, if you put, even if you put B 0.5 and P 0.5, you only get 1. Because it's 0.5, 0.75 you get.
Maybe in the case that all the sediments are transported over the grain, we have the summation equal to 1, plus some parts transported by bypassing and some other transported by grain.
Let me see, to get 1 here, we should, because if you put B 0.5, yeah, if you put B 0.5 and P1, you get 1 again. But still, if you have if you put a value for both of them that is lower than 1, I wouldn't say that you get 1. Let me think about it. No, I wouldn't say that. If you to reach 1, you have to put at least one of the two at the unit value. I would say. Because, you know, it's clear, if you have, I don't think you can get, because, no, you have to put at least one of them in the unit value. But okay, this is a standard function, you could try to...
Yes, because then it's the fraction of the sand that is transported over the grain.
Yes.
So in the case that all the sand is transported over the grain, the summation of B and P should be equal to 1 maybe. And if there's not the 100% of sand is not transported, the summation shouldn't be equal to 1.
Yeah, but the problem is that, let's suppose that you have the summation of P and E that is 1. Let's take 0.5 and 0.5, okay? This means that you have 0.5 of it that is transported by bypass, but the other 0.5 is not completely transported by permeability because it's only half of it that is transported by permeability. So you don't get 1. You don't get the total amount of transportation of passing by if you don't put one of them at 1. Okay, so at least one of them must be 1. Okay, here there is a suggestion for the bypassing factor, but don't take it as a strict rule, okay? Basically, it says that if we indicate with DG the sea depth at the groin seaward end, the groin toe, and DLT is the depth of active longshore sediment transport. What is the length, the depth of active longshore sediment transport? It means that above the depth DLT, you don't have any sediment transport anymore. So when you move offshore and you reach a depth DLT of the ocean, you don't have any sediment transport anymore. Of course, if this depth is equivalent to the depth of the groin at the toe, it means that the groin is extended over the active length of the segment transport, which means that you don't have any bypass. Okay, so if we indicate with D and T the depth of the sea here, and we indicate with DG, this is C, DG the depth of the groin here, DG, groin, It means, what is DLT, remember, is the depth of the ocean where we don't have any more sediment transport along shore. It means that the groin is extended up to the end of the active beach. The groin is extended beyond the end of active along-shore sediment transport. And therefore, it's clear that if I extend the groin up to the end of the along-shore sediment transport, I don't have any more bypass. And therefore, this relationship up there means that if you have dg equal to dlt, bypass is 0. Because, again, it means that the groin reaches the end of the active beach. But the problem is, how can I estimate this depth? So it's a bit of it's an empirical relationship which may give an indication. And here you see that there is written that dLTB, the depth of the active and along-shore sediment transport, can be assumed to be about 1.6 times the significant breaking wave height. Be careful because this is very empirical, okay? It can be an indication, but...
So, I don't understand. The DLT is the depth at the top of the groin of the sea?
No, DLT is the depth of the ocean.
Of the ocean? Yeah.
At the end of the sediment transport.
Okay. So we
And
don't
then-
have sediment transport here.
Sorry?
We have sediment transport or not?
Up to DLT.
Yeah. Ah, okay.
Okay.
So the like a limit.
Yeah, so let me make a drawing here. So let's suppose that you have a coastline without groins, okay? And let's suppose that we know what is the distance to which this is land. Let's suppose that we know the distance, DLT, not the distance, sorry, the depth of the ocean at the distance where I don't have any more sediment transport, and this is DLT. So if you want, you can call this LLT, which means length of the active zone, okay? And here I have a depth at the end of the active zone, I have a depth DLT. Okay. Now let's suppose that I build a groin. And let me assume that it is extended up to the active sediment transport. Okay? In any case, I build a groin and I indicate with dg the depth of the groin at its offshore end, which is of course related to the length of the groin, Lg. It is of course related because if the groin is short, the depth of the groin will be lower. If I want to increase the length of the groin, I need to increase the depth of the groin at the end. Okay? Now, what does it mean if DLT is equivalent to DLG? It means that the length of the groin is the same than the length of the active zone. So the fact that they use the depth, the ratio of the depth there, is just another way of using the ratio of the length of the active zone in the groin. Okay?
So the DLT is related to environmental behavior, and DG is related to
It's designed.
groin structure.
Yes, it's designed. DG is designed by you because you design the length of the groin, and therefore, by knowing the geometry of the beach, you derive DG. Okay? And the length of the active zone, this is more difficult, meaning that you can estimate it, for instance, if you go into the sea and you see when you don't have any sand anymore. But this is really, I mean, it's really something that it's complicated, and also the empirical formulation, it's complicated. I give you an example. If you go on the Adriatic Sea close by here, and you have sand for about 1 kilometer, you can walk into the sea for hundreds of meters, and you still feel that there is sand beneath your feet, because it's very gentle, sloped. We cannot build groins that go into the sea for hundreds of meters. Usually we build groins that go into the sea for some 30 meters. Still, we observe that the bypassing is limited. So you don't, in order to reduce bypassing to zero, you don't have to go up to, it's not linear. This relationship seems to indicate that it's linear. It's not linear. I mean, the reduction that you get with the drawing of a long short sediment transport is not linearly related to the extension of the groin, like it seems from there. Because bypass is a linear relationship depending on, it's linearly dependent on the DG, which is not. So it's just an empirical relationship, and I suggest you that you try to see what happens in other patterns of groins, and if you want to take a precautionary estimation, my suggestion is not make a groin that goes into the sea for hundreds of meters, just take a bypassing factors that is a bit higher. There are some models that use empirical formulations to estimate other empirical formulations, not as simple as this one. And in particular, there is a model that is very popular, which is called Genesis. It's not the model that Gabriele Gaeta will use with you. And this model, I mentioned it because it's widely used. And it uses empirical relationship for computing the bypassing. Okay. Now, let's talk about, again, on groins, on the stability of the armor units. This is a lecture that I published today. These are tripods, by the way. Published meaning that it's visible for you since yesterday night, and it's already in IOL. These are tripods. You see that these structures, they are widely used. The reason why people use these structures, because they are very stable. With this form, they basically get into each other, and they are very stable. They are permeable as well. So if you want permeability and stability at the same time, these are widely used. But a relevant question is armor unit, whatever it is, a tripod or a rock boulder, is it stable? So I think that Professor Archetti mentioned to you the Hudson formula. The Hudson formula is an empirical formula for estimating the stability of breakwaters and groins. Hudson formula is recalled at the end of this lecture. So it's visible there. I just wanted to recall it, but at the same time I wanted to give you another example of empirical formulation for deciphering the stability of armor units. This empirical formulation is rooted in the fluvial hydraulics literature and is extended to the coastal engineering literature, and it's the sheath criteria. So what is the reason why I want to mention to you the second empirical formulation? Because it's based on a physical assessment, physical analysis of the processes that are involved in stability of units. And then from the physical assessment of these processes, an empirical formulation is derived. Because as we will see, the physical assessment includes some parameters that are difficult to estimate. So let's make reference to this sketch. In this sketch you see that you have an ideal structure of a groin with an armor unit on the side that is located there, and let's study the stability of that armor unit. Keep in mind that the shape here is, for simplicity, is like a is depicted like a rectangular shape, but the shape may be whatever. We will see that there are coefficients that allow us to take into account the shape. So, this armor unit is subjected to its own weight, which is a stabilizing force for what matters, the component that is perpendicular to the side. So, let me just make another sketch here. So, the slope angle is beta. So we have this armor unit, which has a weight W. This armor unit is immersed. Let's suppose that it's immersed because when it's hit by waves, it's immersed. Okay? So, in order to compute its weight, we have to multiply the immersed weight. So, let me see if I have another black. Okay, this is much better. Let me use it. Okay, W is equal to gamma S. What is gamma S? It's the specific weight of the armor. So if it's a boulder, it's about 2.6 tons per cubic meters. Okay. Minus the specific weight of water. Then let's multiply it by a characteristic dimension squared. The characteristic dimension is, if it is a sphere, it's the diameter of the sphere. If it is a boulder with a particular shape, we have to identify a characteristic dimension. And depending on the geometry of the boulder, we can identify a characteristic dimension. And then we can multiply everything by a coefficient C1, which is a shape coefficient. So if it is a sphere, you know that in this case is 1/6 pi, I think. C1 is 1/6 pi, if I well remember. Not really sure. No, it's not 1/6, no, it's 4. Okay, let's say we can identify for a sphere the expression for C1 for proportionality coefficient that depends on pi plus some numbers. I think it's 4/3, not 1/6.
Sorry, could you explain again what is D?
D is a characteristic dimension of the boulder. If it is a regular shape, let's suppose that it's a cube, it's the dimension of the cube, okay? The side of the cube. If it is a sphere, D is the diameter of the sphere. And immersed weight, I think you got it, and C is a proportionality coefficient which depends on the geometric shape of the boulder. Okay, this is W. As I said, there is a component of W that is perpendicular to the slope, and this component that is perpendicular to the slope, it's, so we have a component that is, and let me make it longer. There is a component that is parallel to the slope and a component that is perpendicular. The component that is perpendicular to the slope is stabilizing. The component that is parallel to the slope is destabilizing the boulder. Okay, the component that is parallel to the slope is W cos delta. Why W cos beta? Because the angle here is beta. The component that is parallel to the slope is W sem beta. Okay, now we have the action of the wave. The action of the wave is given, let's assume that it is a stabilizing force when the wave runs up. Okay, so the action of the wave here, it's called F, and this is proportional through a constant of proportionality C2 to the area of the unit, which can be expressed as a characteristic dimension D, again, squared. And then there is, let's multiply this by the shear stress that is induced by the wave. So the wave that is arriving over the boulder exerts a shear stress. So what is here the problem? We are not concerned by the boulder that is dragged downward. We are concerned that the waves approach the boulder and may remove it by pushing it up. So I'm not concerned by the boulder again moving down. I am concerned by the boulder moving up. Okay? And therefore, let's consider that in this perspective that the destabilizing force actually is given by the wave. And of course, what happens is that if the boulder is removed, pushed up, then when the wave, then it's removed from the groin. So basically, after it has been removed, it goes down when the waves comes back. Okay. So, but what triggers this displacement of the boulder is the wave running up. It's not the boulder by itself that is unstable. The boulder without the wave is stable. And then stability is undermined by the action of the wave. And the way it's undermined is that the boulder is removed by a force that is pushing it up. And then, of course, it doesn't stop at the top of the groin. Then once it's removed, it's taken by water into the sea. Okay? So, what I want to study is the conditions under which there is equilibrium between these forces, because when there is equilibrium, it means that we are at the very close to instability. When the action of F is exactly the same, that the component of the weight parallel to the slope plus friction of the boulder over the groin, then we are at the limiting stability, as we say. Okay, so we are interested in the condition in which F is equivalent to W sem beta plus friction, and the friction is given by W cos beta, which is the component of the weight of the unit that is perpendicular to the side, so W cos beta, times the friction factor, that is tan phi. Let me see if everything is correct. Okay, let me move forward. I think it is correct. Okay, so the friction factor is given by, as you may remember, the tangent of what is called the friction angle. Okay, good. And then we can substitute for F. So this is beta. For F, we can write, we can substitute this expression here. So we can write C2 d squared tau is equivalent to W sin beta plus W cos beta tan phi. This is just an equilibrium of forces. And this is a condition of limit stability. So we are at the limit of stability. Just let me make